molecular systems biologist, Eric Davidson.
Thank you. Yeah, I'm sorry that I chose such a long title, but I really didn't know how to shorten it up. But it doesn't matter. I discovered in the lectures in the morning that biology is such a different thing from physics. And so to contradict a theory, a result of 4 by a result of 4.0016 is something unheard of in biology. People would only laugh. But I really enjoyed this and I learned a lot in the morning. And I thank the speakers again. So I'm coming now to my biology. So first, the few remarks on revolution in science. The term revolution was used, it became also clear in some of the lectures, used for great changes or great advances in science since the 18th century. Lavoisier in 1773 already used this term, but only in correspondence. He never used it in print. The term became much more common in the 19th century when the British polymath William Whewell used it as a matter of course, describing the work of Lavoisier. And as we heard before from Jemima, Alexandre Poiré, the Russian-French philosopher, wrote, I thought in 39, you said 61, so I didn't have the time to check, used the term the scientific revolution for developments in astronomy and physics in the 16th and 17th centuries. Thomas Kuhn's The Structure of Scientific Revolution of 1962 made this topic very fashionable in the late 20th century. I'm sorry now to philosophers who are here. I just repeat for those who are not so familiar with his work few things of Kuhn's publication, or Kuhn's book. So, according to Kuhn, scientists are normally doing normal science. That is a term. And that means they are solving puzzles within a paradigm. And paradigm was never defined. It can be a theory, it can be many theories, experimental approach or whatsoever. And he also thinks this is an attempt to force nature into the conceptual boxes supplied by professional education. And normal science can be interrupted from time to time by scientific revolutions, and they are replacements of an older paradigm by an incompatible and incommensurable newer one. Jemima connected this incommensurable to linguistics, which I found quite interesting. Anyhow, that means they cannot be measured with the same measure, and therefore can also not be compared. And Kuhn thought these episodes don't arise from the accumulation of knowledge, and that they are relatively sudden and unstructured and not designed by rational debates. To Kuhn, progress exists only in normal science and not between paradigms. And there is not one paradigm is not truer than another paradigm. And scientists also do not aim at better representing and understanding reality. So Kuhn's book, and I wouldn't have talked about Kuhn at all if not for the fact that this Kuhn became so this book became so influential. At first, it was not cited in the sciences, only in the humanities, and had quite a large impact on them. But then, after 1995, about the number of citations increased drastically, also critical citations, as this graph shows. And this graph was constructed by my student, Daniel Sommer, who can't be here today because he represents the university in Geneva, but he will be here tomorrow. And in the last 10 years, this book had 10,000 citations, including the sciences, in politics, in the humanities, in journalism everywhere. And recent examples of scientists who cited Kuhn is Carlo Rovelli. I think many may have seen this essay in Nature. He wrote that, he entitled it, "Theoretical physicists are in thrall, are slaves to a misguided mindset that allows viable ideas to be advanced only by overturning what already exists." And Rovelli is very critical of that. And I cited Doug Irwin in the morning. Some biologists still dream of a paradigm shift in evolutionary biology. And more recently, is an AI revolution looming towards a Kuhnian revolution in AI? And that does not mean Kuhnian revolution in science through AI, but in AI itself. My goals here are to use the work of Eric Davidson to challenge Kuhn's ideas about scientific revolution and the non-existence of progress, and to present the concept of the conservative revolutionary, which I think some of the scientists we heard about this morning fit in this category. Then to outline the consequences for science and scientific truth should AI lead to a genuine Kuhnian revolution. So my first point, Eric Davidson's revolutionary new mechanistic approaches in development and evolution. Eric Davidson was the founder of molecular systems developmental biology. He died 10 years ago, and that's why we devoted this workshop to his memory. Davidson was also a very strong supporter of this, of our center, the Jacques Loeb Center, and we see him here on the picture, sitting on 2 occasions, giving lectures in the Loeb Center. And his experimental object was shown on the right side. It's not a fish, but it is a purple sea urchin. So first, molecular developmental and systems biology. He was a pioneer in the transformations of biological research following the possibility of genome sequencing. And here he was the first to use large amounts of DNA sequencing data in studies on development. He was also the founder of the concept of developmental gene regulatory network, and that, according to him, executes the cascade of molecular mechanisms that transform an egg cell into a complex creature. And we see here a diagram of a network in which, of 3 germ layers, in which a regulator, it is organized hierarchically, and regulatory genes influence regulatory genes on a lower level by transcription factors. According to James Briscoe, he is also a systems biologist in London. According to him, the network model provided a mechanistic and causal explanation to a complex set of gene regulatory events. And in the end, a few years before he died, Eric transformed the network into a computational engine, and he did not only simulate the experimental results in the computer, but he compared the predictions to direct experimental observation. And on the right side down, you see the diagram, and the 2 left, you cannot see that, the 2 left ones show that there is a near confirmation of the results. And again, in physics it would not count as a confirmation, but in biology it does count as a confirmation, though there were some things different. So Davidson also spoke of epistemological revolution in systems developmental biology. Now I come to evolution, and here Davidson was one of the first biologists to link developmental and evolutionary mechanisms, and his long-term collaborator, Doug Irwin, who will speak here tomorrow, he said that happened many years before Evo-Devo emerged in the 1980s. Also, Eric, I think some of persons Jemima mentioned, focused on the origin of variation. He did not talk much about the selection or type of selection, but on the origin of variation, that is the generation of novelty. And together with Doug Irwin, he developed the causal mechanistic idea that the evolution of body plans or body architectures can be explained by changes of developmental gene regulatory networks. Did not come here. Sorry. And with this theory, he contradicted central claims of the so-called modern evolutionary synthesis, which was a prevalent theory at that time. And these claims are that small genetic changes in natural selection are sufficient to explain all evolutionary events, those of microevolution within a species and of macroevolution beyond a species. And the second claim is that evolution takes place in a steady incremental process. And Eric based his contradiction on a couple of things, but most importantly on experiments, true to his mechanistic approach. And for example, he derived from the fact that gene regulatory networks are hierarchical, that some changes have far larger effects than others, those in the lower level of the hierarchy. And he also showed, and that is most important, that many genes of a developmental network change rapidly, but others are very stable. And he termed these stable parts kernels, and they consist of highly conserved regulatory genes. And he concluded that selection does not result in a continuous adaptive change, except in at the network periphery. That means in some properties, in some phenotypes within the species, color and whatsoever. So I come now to my second point, and related to Eric Davidson, namely his conservative approaches. Eric Davidson very much appreciated the history of science, and actually that is why he came here every year to almost all of our international workshops, as long as he was alive. And in this appreciation, he followed the advice from his teacher Heilbrunn at the beginning of his career, or when he was still a student at the University of Pennsylvania. And Heilbrunn introduced him also to the work of Theodor Boveri and Edmund Wilson, and mainly to the concepts of the genomic determination of heredity and development. And that was around 1900, that means more than 50 years before Eric heard about them. And this impressed him so much that, and he was convinced of the importance of these concepts, that he placed his own approach in this old research tradition. He adapted his novel methods and far-reaching general goal, namely a mechanistic explanation of development and evolution, to the traditional laboratory research. And that means he combined his use of large genomic data sets with painstaking perturbation experiments and causal modeling, and thus placing his approach within the framework of traditional epistemology. He was, that is also very important, extremely critical of so-called revolutionaries who want to discontinue the traditional scientific method. And he wrote in 2014, 2 years before he died, 1 year before he died, making databases as doing science is far devoid of explanations of mechanism. And it is not even aimed at any explanations at all. And he discarded this from science. Davidson also used generally accepted epistemologies. For example, observations and descriptions that were brought into science by Francis Bacon in the 17th century. And he gave it a new meaning in the systems approach, where the whole interaction system cannot be studied before all of its components are correctly measured or observed. And the second is very important for Davidson, the philosophy of causal mechanism, which became widespread in experimental biology since the 19th century. And it was basically an explanation of how something works and why. And in his case, it had to do with a genome and causal analysis of the underlying process by which the genome, the genes encode transcription factors in space and time. Space and time, not in a relativistic manner. So the other influence that was important to him was Popper, and as can be demonstrated by his strong, Davidson's strong emphasis on hypothesis, even bold ones, predictability and hypothesis testing. And but one has to say that, like many scientists, Davidson created his own epistemology. I think Einstein actually advertised that. He said, we scientists cannot be pure followers of one epistemology. We have to use what we use for our different purposes. And so in Davidson's epistemology, induction was merged with a generation of bold hypotheses and falsificationism, something that Popper would have absolutely forbidden. Davidson never talked about Kuhn, and I didn't find any mention of him in his work. But Davidson's work was an implicit contradiction of Kuhn's idea of science and revolutions. And it was, for example, in the emphasis on the necessity of basing his revolutionary research on existing knowledge. And second, in his belief in scientific progress and the comparison of theories or paradigms. Thus, he was convinced that his causal mechanistic systems model of early development was would lead to a much better representation of reality. We have to remember that Kuhn, and this also in his postscript to his third edition, in all following editions, that he wrote in order to respond to reproaches of relativity in his relativism in his writing, in his book. He wrote, or he made clear that later scientific theories can be better, but only for solving puzzles. That's what he also said in the book. Puzzles within a paradigm. But they cannot be a better representation of what nature is really like. So Kuhn stuck to this idea also in his postscript. And I think we can see in the history of science that at least most basic scientists have tried to represent and understand reality, the physical or astronomical reality or that of organisms, better than before. They have been goal-oriented, and there was a will to progress in almost all the scientists, for sure with Eric Davidson. And I cite here from Einstein and Leopold Infeld's book, The Evolution of Physics. They wrote, without the belief that it is possible to grasp the reality with our theoretical constructions, there could be no science. Ron, I don't know whether you agree, but this is what I told you before. I come to my last point. Will big data science and AI lead to a genuine Kuhnian revolution, and what consequences would this have for science and scientific truth? I begin with big data and a quotation from a conclusion of a ERC project some years ago, which says, the new paradigm, data-intensive exploration through data mining, challenges the established knowledge-driven deductive approach, ushers in a new era of empiricism in which the volume of data, accompanied by techniques that can reveal the truth, whatever that means, enables data to speak for themselves, free from theory. A science under this new paradigm that is based solely on data and their correlation would give up the search for causal mechanisms and would render the acquisition of knowledge obsolete. And this would be indeed a disruptive Kuhnian revolution, if that had happened. But AI is, as we all know, much more advanced. And AI, I use here a very simple definition, methods for acting in science based on huge amounts of data and equations or algorithms. So in order to get a little bit an idea, I'm not going deeply into the subject. It would require much more time, and I haven't done this research yet. So I asked 5 questions. I asked it in the Google search machine, but as now happened recently, we are always given an answer of AI first, which is also, I think, a development which is bad. So this AI answered to my questions. So will there be hypothesis in AI-driven science? Answer, the role of hypothesis in science is transforming, not disappearing. AI is shifting from being solely a tool for testing human-generated hypotheses to an active partner that helps generate novel, data-driven, again, data-driven and often alien hypotheses at a speed and scale impossible for humans alone. Second question, what is scientific explanation in AI-driven science? In AI-driven science, an explanation moves beyond just prediction. I did not ask for prediction. It's about using explainable AI to make complex AI models transparent, revealing why they find patterns or suggest hypotheses. And then I asked, what is causal explanation in AI-driven science? And the answer was, I can't generate an AI overview right now. Try again later. I'm sure if I had pursued this, I would get another answer, but I just leave it as is, and I did not pursue it also. So what, first question, what is the role of experimental testing in AI-driven science? It is actually quite interesting. The answer, experimental testing plays a crucial role in AI-driven science by validating and refining AI predictions and optimizing the experimental process itself. AI algorithms can simulate experiments, but real-world physical testing is necessary to confirm these predictions. One can say, at least for the time being. And the last question, what is truth in AI-driven research? In AI-driven research, truth is complex. That is, by the way, an answer you get always when they don't really know what to say. And is defined in 2 ways. As ground truth, which is the verifiable real-world data used to train and test models, and as algorithmic truth, which is the probabilistic output of an AI based on its training data and architecture. Okay. My question, which I didn't want actually to ask AI, but I did it in the end also, is I wanted to ask you, will AI-driven research lead to a Kuhnian revolution with the new meanings of hypothesis, causality, and truth? So AI answered, yes, many experts and philosophers of science argue that AI-driven research is a potential catalyst for a Kuhnian revolution or is already creating a paradigm shift in science. This shift challenges and potentially redefines the fundamental concepts of hypothesis, causality, and truth. And the last question, which I just leave in the room, will science become then a tool for puzzle solving in AI-driven applied research? So I have 2 more small concerns regarding the rise of AI. Jelinek is not here, right? No, he wanted. Anyhow, the first comes from a journalist. David Horowitz is the editor-in-chief of the Times of Israel, an English-speaking newspaper. And he wrote a few days ago an article with the title, An Editor's Flawed Human Ramblings on AI, Journalism and the Disappearance of Truth. And he wrote, I feel a growing inability to distinguish between what's true and what isn't on our phone and computer screens. For example, picture, for example, quotations, for example, descriptions, and so on. And in time, and that is the most worrying part, a growing indifference to this distinction. I just can hope it will not go in science like that. And Sarabach here from biology whom I talked to some days ago, and asked him what is AI in your mind a revolution. He said AI is a revolution because you can do what you could not do before. Clear definition. And then he said it is also not a revolution, and he means here not revolution, but he means here it is also bad, because students know less and less, read less and less, and have less knowledge. We have the knowledge to deal with AI. We remember things, but students don't remember things. They believe they can find everything in AI. And concerning this remembrance, other colleagues confirmed him. And I have to remind us that knowledge and memory are the basis for critical thinking, for creativity, and also for dealing with AI. So, do I have time?
You have 12 minutes.
Until half an hour? Oh, altogether. No, I finished in 1 minute. So, in my concluding remarks, I come back to Eric Davidson and Thomas Kuhn, and present Davidson as a non-Kuhnian revolutionary. He was certainly a revolutionary because his work led to a conceptual and methodological breakthrough in molecular systems biology of development. I think a revolution can also be the opening up of completely new fields. It doesn't have to contradict something that exists. Second, he contradicted, and here he indeed did contradict doctrines in evolutionary biology. But he was a conservative revolutionary. He followed generally accepted epistemologies, and he placed his research within an old conceptual frame and showed, in his words, the breadth and depth of the resolving power of the new precepts of systems biology when synthesized with the old precepts of traditional scientific logic. And he combined broad knowledge and critical rationality with a passion directed towards understanding reality. And let me end by a quotation of paleontologist and science writer Steve Gould. It's a little old, and the first part doesn't really apply anymore, but I cite it anyhow because of the last part. In a world awash in New Age mysticism and old-fashioned anti-intellectualism, and I would add now a new-fashioned uncritical belief in AI solutions, and the emphasis is on uncritical. I don't mind using AI, of course not, I will not talk about that, but the uncritical belief in AI solutions. It may be something of a cliche to point out that salvation requires rationalism now more than ever, and equally obviously, such salutary attitudes need to be embodied in passionate and persuasive individuals and not in abstractions and collectivities. Thank you.
Thank you, Rita. We have enough time for questions. Yes, Sebastian.
You just said uncritical belief in AI.
Yes.
Okay. I agree with that. Now, maybe the problem would be uncritical belief in new paradigms and new models. If AI is a revolution.
Sorry, if AI?
So,
if AI is a revolution, and we can take AI because it's very useful, but the bad part will be an uncritical belief in AI. So wouldn't that work for any other revolution? The uncritical belief in the new paradigm or in the new model?
The models that I have presented here, they could all be tested experimentally.
Yes, but in a certain sense, they all, let's put it like this, all the paradigms are models, bigger models, smaller models, but they are not completely free of errors when you are going out of the model. So for instance, if you are doing quantum mechanics, obviously we heard this morning that when you are going in the direction of relativity, it fails. So you cannot do uncritical belief of any new paradigm. including AI, of course.
I am not against speculations. And what you just referred to, I think, were some speculations or something. But at some stage, it must be shown whether or not they correspond to reality. However you will do that. In biology, you do it by experiment.
Yes, my point is that any new model, any new theory or paradigm has limits, including AI, of course, but knowing the limits of a model is as important as knowing the model itself.
I agree.
Would you say that this is critical for revolutions as well?
No, I agree with that. You have to know the limits of your model. And you have to extend it also if there are contradictions.
Yeah, so maybe it's more as a comment than as a question, but the point is comparing AI as a revolution to any other scientific revolution. The uncritical use of that is the biggest problem, including if you take Kuhn's idea as a revolution itself. The uncritical use of Kuhn's model is what brings the problems in the use of the model.
I think the model is basically flawed. But
we
may disagree. We had this discussion already. Yeah, I think there is nothing so far of a revolution like he said. Maybe, look, Lysenkoism in the Soviet Union, they discarded the whole of genetics altogether. It was forbidden. That was kind of a Kuhnian revolution. But in the end, when the people were free again to decide what they wanted to do, they got rid of this because they realized that it doesn't respond to reality. They cannot make better crops with this model, with this Lysenko model. So that would be an example of a Kuhnian revolution. But I don't see any other.
Yes, Emilio, please.
Yeah. I'm not sure I
You
completely
need to activate the microphone.
I'm not sure I completely understood, but it appeared to me that you draw some contrast between collection of data, which AI is very good at, and causal explanation. Am I right? That you see a contrast there?
No. Sorry, the contrast is only when you stay with a collection of data and correlate and don't do causal analysis. But the collection of data is very important.
Yeah, no, I understand, but I thought you were saying that AI is good at collecting data and may not be so good at causality-driven explanations. And I think that there is today a lot of computer work on causal networks, and so potentially AI can identify causal processes and distinguish them from randomness and from accidental correlations and from this sort of thing. I think we're not yet at the point where we can learn from AI about the mechanism of this causal process. But I think we can use AI to identify causal processes.
Maybe it's possible. I am not aware of that. I just see that the answer to my question to AI was that they have a different understanding of causality.
Which is what?
No, they wrote to me. We have
Yeah,
to,
I know, but how to interpret their answer? What is this different concept of causality?
it is not to find out how something works and why something works, but it is somehow related to the AI analysis itself. They said before that we will understand what they suggest and what something like that. It is not related to reality. I don't see that. At least not now. Not in this definition. Maybe it is in people are using it in this way, but I wouldn't know. As I said, I'm only at the beginning of the research, So I don't know more. I just was very worried about what I found. You know?
Okay, thanks.
Yes.
Yeah, I think I could give an example that's relevant to this. A former postdoc of mine, Mike Garvin, and a group of us looked at a huge database on autism, and we found literally hundreds and hundreds of structural variants. And actually it relates to Eric Davidson, because when we looked in detail at some of these variants, almost all of them affected gene regulation and cascades of gene regulation. And we found, in fact, these are actually high levels of variation in this. That's somewhat contradictory to his idea of a kernel. These things can really change dramatically. And we used AI because the data set was just so massive, and AI identified 3 subsets of these. So they were genetic subsets in the sense that these were the genetic markers that came together, but they also, AI identified that these 3 subsets each affected a different biochemical pathway. For example, the nonverbal autistic children were affecting in the kind of urine pathway. And then another group, medical group, that we had nothing to do with, saw our paper. They had a large body of children with nonverbal autism. 60% of them had the defects in the kind of urine pathway that we had predicted from the AI model. So I think you're already at that point where AI is generating hypotheses. And these hypotheses are testable in a Popperian sense too. And this is just one example. But it's also showing the huge role of structural variation in regulatory networks that, unfortunately, Eric Davidson didn't have the technology to study at that time. And it's actually making it, I think, more important, because we find a structural variant is 50 times more likely than a nucleotide variant to be associated with phenotypic variation.
I just heard recently from Doug Irving that the idea of kernel was again confirmed under different names, and that is still a valid concept. I mean, I can only say what he said. I met him in September, you know, and he will talk tomorrow. Okay, thank you, but thank you.
Thank you very much, Ute.